recorded.
Okay, so to go back 1 second, just to reiterate, yes, there will be instances on the test where you'll be asked to calculate the z, so you'll be given a mean and a standard deviation. Mean and standard deviation. You'll be asked to calculate z-scores. You'll be asked to find areas in a normal distribution. I always like sketching these. It makes it easier to avoid getting them wrong. You'll be asked what's the area below this amount, what's the area above this amount, and you know from your table. We'll actually maybe practice a couple of those as we're moving forward. What's the area between these two? Some of the questions will ask you to use the empirical formula, where it's whole numbers of z-scores. Some of them may force you to use the z-table or Excel, whichever one that you would prefer. Okay, and as far as binomial distribution is concerned, two kinds of problems might turn up there, and one is this kind, where we're looking at the probability of a specific outcome given a certain sample size. So for instance, if we sample 4 people randomly in a population that has a probability of being a prevalence or a probability of being diabetic in a population of 10%, 0.1, what's the probability that none will be diabetic? And as we just said, binom dist was a function you would use, parentheses, 0, right, is the number of successes in this case, right? Forget about the or less yet. Okay, 4 is the number of people that you sampled, your sample size. 0.1 is the probability of any of those individuals being diabetic, and you would answer false for cumulative because you're only looking specifically for the probability of no one being diabetic, or 1 being diabetic, or 2 being diabetic. Okay, then on the other hand, we might ask you, what's the probability of 1 or fewer being diabetic? Well, in that case, number of successes is 1. 4 is the sample size still. 0.1 is the probability. But we say true there because it gives us the probability of 1 or 0. 1 or 0 added together, right? Cumulatively, right? So that's why we would say true there. And then if we asked you the probability of 2 or more, right? Well, that excludes 0 and 1. So since you already figured out 1 or 0, you just subtract what you got here from 1, and that leaves you with the probability of 2 or more, and so on. So and the other place where you might see binomial distribution is occasionally we use a normal approximation to the binomial distribution. So let's say, for instance, that we're going to sample people and ask them if they're left-handed or they're right-handed, right? And we find that in this population, that 30% of the people are left-handed in this population. That's pretty high, but let's say it's 30%, right? So let's say we go and sample 100 people, right? Well, our expectation is that if we did this over and over and over again, on average, we would get n, the sample size, times the probability, or 30 people out of 100 being diabetic. Sometimes we'll sample 100 people, we'll get 28, sometimes we'll get 32, right? But on average, we would get, if we did it many, many times, we get an average of 30, n times p. Well, we could draw that distribution, and it looks, although it's not exactly like a normal distribution, it looks very much like a normal distribution. We can actually use it to approximate a normal distribution. So if I asked you, what's the probability that we would get 25 or fewer people who are left-handed if when we sample 100, what's the probability that would come up? Well, we got the mean, right? The mean is mean. I'll just call it X bar instead. The mean is 30. We need a standard deviation in order to figure out a z-score, don't we? Well, the standard deviation in the binomial distribution is the square root of n. I'll do it as p times 1 minus p times n. Okay, n is the sample size, p is the probability of a person being left-handed, and 1 minus p is the probability of them not being left-handed. So that turns out to be a square root of 0.3 times 0.7 times 1, what's our sample size again? 100 times 100, right? This is 0.21 times 100. 0.21 times 100 is 21, square root of 21. Let's see, square root of 4, 4 squared is 16, 5 squared is 25. So I'm going to say approximately 4.5. That's approximately 4.5. So if the standard deviation is 4.5, remember that's approximation, right? Then you can go here and you can say, wow, now I can say a person at 25 is over here. So the z-score for 25 is equal to 20. Excuse me, is equal to 25 minus 30 over the standard deviation, which is 4.5, which is 5 minus 5 rather over minus 5 over 4.5, which is, I'm going to say, roughly 1.2, 1.1, roughly 1.1. So you can go to your z-table and see what area a z-score, negative 1.1 actually, because it's to the left, what area a z-score of negative 1.1 represents. And that's the probability that you would get a sample that has 25 or fewer people who are left-handed if you sampled 100. And if I ask you what's probability we get 25 or more, it's just going to be 1 minus that because it's the remainder here. Right? So you might get a problem like that where it involves this guy by a normal approximation of the binomial distribution, or a specific outcome where we ask you what's the probability of where it's a count, where it's 3 or 4 or 1 or 12 or whatever, or fewer, and we ask you and we give you give it in a form where you would use you would be looking at repeated samples of that size 4, size 10. And in this case with binomial, when we have very large numbers, you could do this way. Okay, you could do it the other way too, right? But you get a slightly different answer. I'm make sure I accommodate both. So at any rate, meaning that there's no binary outcome. I'm not sure what that means. Is false always for 0? No, you can also use false. Let's say I asked you what's the probability of getting exactly 3 out of 4 people in this outcome. Exactly 3 out of 4 people that are diabetic. So you're not interested. See, if you put true in there, it'll give you the probability for 3, 2, 1, and 0 all added together, right? So if you only want the probability for an outcome of exactly 3 people out of 4, then you put false in there and it gives you the probability only for that specific outcome. Okay. So let's move on from there. You know, I have something I'm going to post later on. There are a couple of Word documents. Let me open them up. I think they're in the background here. I got to move this out of the way. Okay, so here's some examples of data types that you might get. For instance, you might go through these. I'm going to post this solutions box, solutions page for this as well, so you can see the solutions to this. Occupation, plumber, so on and so forth, social status. Okay, let's talk about a couple of these. Occupation, right? Plumber, teacher, secretary. That's going to be a categorical variable, right? I'm not going to quiz you guys because it's going to kill time for you to type stuff in. And I want to get through as much of this as possible as we can. Social status. Well, social status, lower, middle, upper class, that's also a categorical variable, but it's a special kind of a categorical variable. It's a ordinal variable. Give that a special name, ordinal, because even though the status has names, lower, middle, upper class, and it's not well defined what upper, middle, and lower class, upper classes. For instance, if we talked about middle class these days, I'm not sure anybody really knows what they're talking about anymore, but what middle class is. Everybody's got a different definition. But we do know that most people would agree that there's a difference between lower, middle, and upper class, that one is higher than the other or lower than the other. It has order, but we can't really define exactly what the differences are. Not everyone agrees on it, right? So that would be a ordinal variable, a special version of a categorical variable called ordinal. Okay, if we want anything that's numerical, for instance, if we looked at community size and I gave you the population of one community is 2,000, another one's 3,500, that would be a numerical variable, right? On the other hand, if I gave you a rural, small town, large city, that would be an ordinal variable, right? If I statewide murder rate, number of murders per 1,000, right? That's a numerical variable. Okay, so you guys can pretty much figure that out. While you got, I don't know how many of you guys were online with us before. I think it's pretty much the same people, right? Okay, so before we went to a histogram, this is a bit more complicated one. It might ask you for 30 days, patients arrived, at least one patient was treated every day. These are 30 days. How many patients were treated in the emergency room on each one of these days? And each of these bins represents a different result for a different number of patients treated per day. Okay, so for instance, the frequency tells us the number of days that we treated. I don't know if I can read that too well. Let me enlarge this a little bit, if I can. Okay. Okay, 5, 6. So this represents the highest, which is 6. We had 6 days during this month of 30 days where we treated 6 people in the emergency room. We only had one day where we treated 13. And we didn't have any days with 14 people worked and moved in and came into the emergency room. So the key here is to distinguish between it's going to ask you a couple of questions. Key here is going to be distinguished between when it's asking you a simple probability, when it's asking you a conditional probability. So a simple probability, we know there's 30 days represented here. And if I ask you what's the probability what percentage of the time of probability that there were days that we treated exactly 6 patients out of the 30 days. How many times a month did we treat exactly 6 patients? Well, 6 patients came up 6 times out of 30 days. So it'd be 6 out of 30. And what's the probability that we treated 4 or fewer patients per day? Well, that happened twice for 4. It happened 5 times for 3, and it happened twice for 2. So that's 2, 5 is 7, and 2 is 9. So that would be 9 out of 30 days, 9 over 30. Now, what about conditional probability? What percentage of the time did we, or how often did we treat? Given that we treated more than I'm going to make it a little easier on myself. Given that we treated more than 10 patients, more than 10 patients means that the only thing we're looking at is days when we treated 11, 12, or 13. Given that we're only looking at the people that times we treated more than 10 patients. In other words, these days, what percentage of the time did we treat 13 patients in a day? Well, you have 3 days that can satisfy the condition. What percentage of those 3 days did we treat 13? Well, only 1 out of the 3 days. So that would be 1 out of 3. Okay, so that's conditional probability. Okay, so here's a bar chart. There's another version of it, and so on, but pretty much the same thing. Okay, here's one. Suppose you have 3% of the population in a given community have attempted suicide. Suppose it's known that 20% of the community are living below poverty. If these two events are independent, what is the probability that a person selected at random from the community will have attempted suicide and will be living below the poverty level? Okay, well, if they're independent, that means that the probability of committing suicide and the probability of being below the poverty level have nothing to do with one another. Then we would multiply these two. 0.3 times 0.2, and we would get 0.06. 0.06, excuse me. 0.03 times 0.02 would be 0.006, I think it is. It'll come up to, right? So if they're independent, you multiply them. Now, what if I told you that they weren't independent? That being under the poverty level makes it more likely that you committed suicide. Well, then you can't multiply these to get the result because one has an influence on the other. It's not really completely independent. One of the ways you could test that is, for instance, in this case, remember we just said that it was, let me see if I can't get a marker up here. better yet, I'll get this sheet here. Okay, let's take a look at this. Given that, 3%, 0.03, have attempted suicide, and that 20% of the population is under the poverty level, the probability that you both, if it's independent, the probability that you both are under poverty level and attempted suicide is going to be multiplied to two of them is going to be 0.006, right? 0.2 times that, move the decimal place over 1, and you get 0.006 or 0.6%. Well, let's test that. Let's say you took 1,000 people in this population, right? And you found out that you asked them, have you attempted suicide? And you would check their income and so on and so forth to decide if they're under poverty level. You find that the percentage of people in this population that satisfy both of these conditions is in other words, the frequency that comes up, both of those conditions are satisfied. It doesn't come up 0.006. It comes up 0.014, right? Well, gee, it's higher than it would have been if it were independent. So maybe there is an association between the two of these. So one way of testing whether they're really independent is to take a large sample from the population and see if it really is this result that you would get if they were independent. So you might get kind of a verbal question on that or something like that. Okay, so this is another version of the conditional probability. I won't go through that again. Okay, so here's something that might have something to do with the z-scores. Okay, the psychomotor index, I think this might have been a homework problem or something like that. A scale of infant development, no, I don't think so. Maybe not this semester, maybe another semester. Scale of infant development approximately normally distributed with a mean of 100 and a standard deviation of 15. This is just a simple test for children's development stage. Find the probability, it's a numerical variable. We know the mean and the standard deviation. Find the probability that the infant's PDI exceeds 103. Find the probability that it's between 97 and 103, and find a z-score for a PDI of 90. Would you be surprised if to observe a PDI of 90? Okay, so let's take a look at this. See how much of this I remember by the time I get to the next page here. So 100, 115. Okay, here's our distribution. The mean is 100. The standard deviation is 15. What's the probability that you would get a value above? This is going to be, I think I said 103. And this is going to be a value of 97. Okay, I'm going to ignore the questions partly, and I'm just going to invent as I go along. Let's see, what's the probability that you would get a score lower than 97, less than 97? That would represent this area in here. But how do we figure that out? Well, we need a z-score, don't we? Okay, unfortunately, it's not an even number of standard deviations. So I can't use the empirical formula. I'm going to have to go to a table or to Excel, right? So let's see. So the z-score is going to be equal to the value we're interested in, we call that x, minus the mean over the standard deviation. So what is that equal to? Let's see, the mean, the value we're interested in is 97 minus 100 over the standard deviation, which happens to be 15. Well, that's minus 3, keep the signs, over 15, which is negative 0.2. Am I right about that? Yes, right? So we have a z-score of negative 0.2. So now we go to our z-table to determine what's the area to the left of 97. In other words, less than 97. So let me see if I can't find the z-score, z-table real quick. Now you can use Excel instead if you want, or you can use both just to check your answers. Oh, I just had it there too. I shouldn't have done that. Table. T-table, I don't know, the z-table. Progress D. Okay. Nope. There we go. There it is. Okay, you use the table in the book, table from that I've given you here, doesn't matter. So negative 0.2, negative 0.2, well, the zero is understood after this, negative 0.20 is going to be an area of 42%, 0.4207. So this area, oops, what did I do there? I turned on the eraser. Oh, I'm using the backside of my pen. This area is going to be 0.4207. That's the area that's involved in here, 42%. If I ask you what's the probability of randomly selected person, infant from this population having a motor score of greater than 97, well, it's going to be everybody to the right of this. So all we would need to do is subtract 0.4207 from 1, and we would have this area in here, right? Well, if I get more complicated, I want something in between here, between 97 and 103. I'd have to figure out a new z-score. For 103 minus 100 over 15 is going to be plus 3. Over 15 is going to be plus 0.2. Now I go back to my z-table. Okay, and we're looking at plus this time 0.2. Plus 0.2 is going to be 5793.5793. So this is going to be this area from here down, right? It's always to the left. From here down, 0.5793. So if I'm interested in this area in between, well, I know that from here down is 57.93%, right? And from here down is 42%, right? So the area I'm interested in is between them, right? So if I just take this larger area and I subtract the smaller area from it, it leaves me with the area that I'm interested in. So all I do is take this number, subtract them, and get a total, whatever it is, 0.1, whatever, 1.5, whatever it is, right? So that's basically the kind of thing that you would probably run into here. Let's see what we have besides this. Okay, okay. So, heart disease leading cause of death in the United States. This one is. Okay. Don't worry about this one. This involves something we didn't talk about this semester. I'll eliminate that when I upload this to Blackboard. Heart disease leading cause of death in the United States, 2024. So 10 people were randomly sampled from all those who died in 2011. What's the probability at least one of those deaths was due to heart disease? Okay, so heart disease was a leading cause of death in the US in 2011. 24% of all deaths. Now, suppose we go in there and check the records and randomly select 10 people from those records. What's the probability that at least one of those deaths was due to heart disease? Well, okay, let's take our sheet here. Let me get a fresh sheet. Let me get rid of this. Okay, so 24% of all deaths were due to heart disease. So if it's random, we would say, if we just go in there and sample completely independent randomly, we would expect our probability that the person we selected is the probability that they died from heart disease would be 0.24, 24%. So now, if we would just go in there and randomly select 10 people, in other words, our sample size is 10, what's the probability that we would get one or more people that died of heart disease in our sample of 10 people? Well, we would use the binomial distribution in Excel, right? Binom dist, right? And I'm going to cheat here. And first, I'm going to ask you, let's ignore this one for now, but I'm going to ask you what's the probability of getting exactly one person out of 10 that died of heart disease? How would I put that into the binomial distribution function in Excel? Well, the way it works is it asks you for the number of successes, the sample size, the probability of any individual having that condition, that disease, whatever, and whether or not it's true or whether it's cumulative or not cumulative. I'm going to put CUM there, true or false for cumulative or not cumulative. If you're looking to solve exactly one, we're going to say, well, the number of successes we want to know is about 1, comma, the number of trials or the number of sample size is 10, comma, the probability is of any particular individual having died in these records of heart disease is 0.24, and cumulative, well, cumulative, if we said true here, it would include everything from 1 below 1. So it means it would include 0, that no one in our sample of 10 people of 10 records had died from heart disease. We don't want that. It asks for exactly 1, right? So we would put false for cumulative here. Just give us a result for exactly 1. If I had written 1 or fewer, right, including 0, then I would have put true here. So what about the probability for 1 or more? Well, the probability for 1 or more is really just the probability for everybody except, in this case, 0. So for that, I would put the probability of 0, comma, 10, comma, 0.24, comma, and it doesn't matter if I say true or false here because it's 0, there's nothing below it anyway, right? So this would give me the probability for exactly 0 people having died out of 10, having died of heart disease. So if I want to know what the probability for 1 or more, it's going to be everybody else. So we just do 1 minus the result of this binomial this. Okay, if I ask you for the probability of 3 or more, well then you would want to know 2 or fewer, 2, 1, 0, right? So 2, 10 sample size, 0.24, and true, so it includes the probability for 2, 1, and 0. And if you subtract that result from 1, you would get the probability left for 3 or more. So you got to be a little bit careful with the way it's worded, so you know that you know exactly what you're going after there. Okay, diagnostic tests. Okay, there was diagnostic tape for prostate cancer that was 95% accurate on on men who have the disease and don't have the disease. In other words, sensitivity and specificity are both 95%. If 4% of the men in the population have prostate cancer, compute the probability that a tested patient has prostate cancer, given that its test result indicates so. Well, you want to know something? That's not the question I would have started with there, right? That's asking you the conditional probability, the conditional probability for a positive test. In other words, what's the probability that you have prostate cancer given that you've tested positive, right? And we know that we have a formula on Blackboard or in the homework also, I think, where if we know the sensitivity, the specificity, and the prevalence, if we know those 3 things, we can calculate the positive predictive value, right? There's other ways we can do that too, and I'm going to open up, rather than do that one, I'm going to open up a different file here, which I'll also upload, that will give you a little bit of an idea on how to handle this. Okay, hang on a second here. Let me see if I can get to it here easily. That's interesting. Wonder why that's grayed out. Okay. Let me double click on it in that case. Okay, here we go. Let's blow it up. Okay. Okay, so let's assume that 20% of the population is hypertensive. I'm going to take this example instead. Here's a frequency table that shows you a population distribution for, this is a contingency table for a diagnostic test. Let's assume that this has been a randomly selected, 1,000 randomly selected population, right? So here is, we have a total of 1,000 people in this population. 200 of them actually have the disease. In other words, the people in this column are the people that actually have the disease. People in this column are people who don't have the disease. And everybody in this row tested positive everybody in this row tested negative, right? So this means you tested positive and you have the disease, true positive. This means you tested negative and you don't have the disease, that's true negative, right? So these others are false. This one is, let's think about it now. Was the test positive or negative? The test was negative and it said you had the disease, so it's a negative test, right? So it's a false negative. These guys over here, they tested positive, but they don't have the disease, so that's a false positive. So look to see, you wouldn't call this a false negative because the test was positive. So it can't be a false negative. It's got to be a false positive, right? So in this case, the sensitivity would be how good you are at predicting you have the disease in people that predicting that people have the disease among people that do have it, right? That's the sensitivity. So sensitivity is 170 over 200, which I think is 85%. 170 divided by 200. 200 people have the disease, you got it right for 170 of them. Sensitivity. Specificity is how good you are predicting people don't have the disease. 800 people don't have the disease, you got it right 720 times out of 800. So the sensitivity is 720 over 800, which is, I believe, 90%. So the specificity, right? The specificity is 90%. The sensitivity is 85%. The specificity is 90%. Well, let's take a look at these people that tested positive, because that's usually what we're really interested in, right? If you how many people in this population tested positive? 250 tested positive. How many of them actually had the disease? Well, 170 out of the 250 actually had the disease. The other 80 didn't have the disease. So the positive predictive value, the percentage of times that it got it right as a positive test, is going to be 170 over 250, right? Which is going to be, let's see, 170 over 250 is 17 over 25, which is 4 times that would be 28. What is that, about 68% or something like that? Somewhere in that neighborhood. What's the negative predictive value? The negative predictive value is among the number of people, among the people that don't have that tested negative. How often was that correct? Well, that would be 720 over 750, right? Which is, I'm going to guess 90, above 90%, whatever it turns out to be. So that's how you would deal with that. So now, you also have an option where you can use, I'll post this, use a formula. I don't have it handy right now. You could use a formula. I'll tell you what, let me look it up. Okay, positive predictive value formula. You also have a situation where you can have a formula where, let's see, negative. Oh, let me look in images. Probably my best bet. Let's see, where is it? I'll provide you with the formula. Here you go. In this formula, you can calculate the positive predictive value if you know the sensitivity, the prevalence, and the specificity of the test. It's a little hinky. You got to be careful, right? So, for instance, in the one we just did, the sensitivity was, I don't remember exactly, I think it was 90%. 0.9 times the prevalence in the population was 0.2, 200 out of 1,000, over the sensitivity, whatever it was, 0.8, was it 0.85? 0.85 times 0.2, I don't remember the numbers, 0.85 times 0.2, whatever they were, plus 1 minus the specificity. Specificity might have been 90%. So 1 minus that would be 0.9, would be 0.1, times 1 minus the prevalence. Prevalence was 20%, so this would be 0.8. So you got to do 0.1 times 0.8 and add that to whatever the sensitivity times prevalence. That's the whole bottom of your equation. And this is the top part of your fraction. So if you resolve that, you'll get the same result as you got from that table for this. Okay, we've gone over this a couple of times in lab and on video and stuff like that. So I'm not going to actually work out these numbers. But the key here is you got to be careful with the numbers you put in there in your math, right, when you do this. And but if you're careful, things should work out. Now, the only other thing that I think, I can't swear that there won't be anything else that we've covered this semester, because we did cover a lot of stuff. You're not going to have anything on the, let's say, don't save there. You're not going to have anything, move this over here. Okay. No central limit theorem, right? No, in other words, no situations where you're talking about repeated samples from a population and the distribution of the sample means and so on and so forth. And what you deduce from that, the thing that we really use that for, the 95% confidence interval, we're going to hold that off until the next test. That's not going to be on there. However, you will likely ask you to calculate descriptive statistics. Okay, now you could use Excel for that. You could use SPSS for that, or you could use R for that. Excel files are .xls, or nowadays it's whatever the other letter is nowadays. The SPSS files are .sav, and the R files are text files. They're usually what are they, .txt or comma delimited, whichever one it is. But I will provide you with versions for all three of these, so you can use your choice as to what you want to use to calculate mean, standard deviation, range, percentiles, right? Interquartile range, right? If there's different ways to calculate it between Excel and SPSS, numbers come out slightly different. I'll accept either one of those as an answer and make sure the range will cover the range of acceptable answers. We'll cover it, and so on. So make sure you're ready to, now I won't ask you to copy from the SPSS file, copy to a Word document, upload it to so on and so forth. I won't ask you to do that because it's going to be kind of tedious to do. And if there's any kind of glitches on the versions of Word or SPSS, you guys know that can be kind of pain in the ass. I don't want to slow you down on the exam and disadvantage people whose computers or laptops or something like that work a little bit hinkier at copying and pasting than other people's, right? So you use these things to determine the answers, and then you'll write the answers into places into Blackboard. So if you've been having glitches with your version of SPSS, and you were thinking, I'm not bringing my laptop because I can't copy and paste well, on my laptop, and I'm not used to the lab ones, you don't have to worry about that. You can bring them, and you can, as long as you can use them to do the calculations, get the results, you'll be able to copy them in. Okay, so I think now's a good time to quit on this. Let me just go to the comments and see if there's anything I missed here. Okay, for those students who can take the entire, how many days will the exam be available? I'm thinking of making the exam available for 3 days, starting on Tuesday, Wednesday, Thursday. You will have a window of 3 hours or whatever the classroom time is, to 2 hours and 15 minutes, whatever it turns out to be, to take the exam. You start the exam, you do it in one sitting, just like the students in class. I guess that's it. You'll just like the students in class. You can access Blackboard for anything you want. Can't surf the internet for answers, but you can access Blackboard, or anything that's linked from Blackboard is fair game also. Like the videos, if you really need to get them, it doesn't take 3 days, not 3 days and 3 hours. That's a long time. In other words, anytime in those 3 days, anytime that's a good time for you to sit down, where you have 3 hours where the dog doesn't have to be walked, the kids are not crying, they're asleep, you had a good meal, you have a drink, your blood alcohol level is low. Anytime in those 3 days, you can start the exam, and from the time you start the exam, you'll have 3 hours, approximately 3 hours, just like whatever time is in class, to complete it, just like the guys that are in class. Is that clear? Does that make sense to you? Okay. And if there's an issue here where, like, you're working, like you're a medical student, you're an intern, and you're working 72 hours continuously during the Tuesday, Wednesday, and Thursday, and you absolutely can't do it, that you can get in touch with me and I'll try and figure out some accommodation. Okie doke. And you guys in class, you nutrition students, unfortunately, your department wants to make sure you learn this stuff, and they want your fannies in those seats. So I'll see you guys on Tuesday. And to some degree, it's nice also because you'll have me there to, if you have any doubts or questions or something like that, you'll have me there live. Unfortunately, I can't stand in front of the screen for 72 hours continuously in case somebody taking it online on Wednesday at 4 a.m. Once they ask me, well, this question over here, can I get a clarification? It ain't going to work for them, So they have the advantage of maybe being a little less stressful situation, and you have the advantage of having me there. Okay, if that's assuming that's an advantage, right? So have a good rest of the weekend. Study hard, do great on the test, and I'll see you guys on Tuesday. Take care. Bye.